Right, I'm just going to give a quick solution guide for how to do leak code 84, largest rectangle in histogram. Given an array of integers heights representing the histogram's bar height where the width of each bar is 1, return the area of the largest rectangle in the histogram. So the way a lot of people sort of approach this problem, myself included, is basically using something called a monotonically increasing stack. All right, so we're going to be using the stack data structure, and we're going to be wanting to keep track of our stack. Should always have a state where we're going to be keeping track of heights, where the heights are increasing and increasing and increasing. And we're going to see why in a second, why that's so beneficial. So our implementation is quite straightforward. We're essentially going to be optimizing by looking for, we're going to be updating our max area variable every time we pop from our stack. And our stack is going to hold all of the potential heights that we want to be using. And every time we update from our stack, pop from our stack, every time we make an update, we also have to make some changes to our stack to reflect what's happening around us. Looking here, I drew a pretty big test case to sort of run through all of the different possible things that can happen as we run through a case. I'm going to skim through what this test case would look like, and hopefully it'll give you a really good idea of why and how this solution works. So I'm going to draw my stack as just this. So every time I add an item to my stack, I'll just write like add 2, add 3, and then pop 3, right? So our stack is going to be holding a bunch of indices, because every time I pop something, I want the indices so I can know not only the height at that indice, but also the width, right? The indices give me the width. So just the indice information is satisfactory. So what's going to happen here is it's a monotonically increasing stack, right? Every time I get a number smaller than when I peek into my stack, I want to remove that larger number in my stack. Until I want to keep on removing until I can find a good place to put my new item and retain the monotonically increasing stack structure. And we're going to look at why in just a second that's such a powerful tool. So first of all, looking at this test case here, if we're looking at, really quickly, just trying to find the answer. 1, 2, 3, 4, 5, 6, 7. So the answer here is just 21, right? I just did that real quick in my head. The computer can't do that. So we're going to start off with our max variable equal to 0. And then we're going to look at this first height, right? This first height is one of our contenders. Maybe, we don't know yet, maybe the max height is attributed, or the max area is attributed to this height at index 0. So what we're going to do for now, well, we don't know yet, we're just going to put it into our stack. It has a height of 4. It's okay. We'll see what has to come, right? And then all of a sudden, we see this 1 that has a height of 2, right? So height of 2 right here. So once we see that, we want to maintain our monotonically increasing stack structure. And the reason for why we do that is because once we see that this second index has smaller height, this height at 1 is less than the height at 0, we know that if we were to look at any of the other possible arrays or possible rectangles from here on out, their max height is bounded right now by this. If we wanted to include this, anything past this one index, the height is bounded by the height of 1, right? This, the height would be 1. This here, or sorry, for the first one, the height would be itself. But here it's bounded by 2, right? Bounded by that second one's height. Here it's bounded by 2 again because it's bounded by index 1. Here it's bounded by 2 again, bounded by index 1. So once we see that we have a height smaller than our previous height, we can get rid of our previous height. That's the whole point of the monotonically increasing stack. Once we see that this one index value has a height smaller than the height associated at 0, then we can get rid of 0 from our, or we can get rid of the height attributed to the index 0 in our stack. We don't need to test 4 anymore. We can just only test 2. Right? Because it's not possible for it to be of height 4. There's this gaping hole right here that's preventing it from happening. So, yeah, that's what happens when we see that this height is less than the previous height. So, but we do need to consider another thing, right? Because when we see this height of 2, we know because it's smaller than this height associated at 0, we know that this height 2 segment, I'm going to use a different color here. This height 2 segment, we don't know where it ends. It could end here. We don't know for now, but we'll know eventually. It could end. We know it should be ending around here, but this starting point is actually incorrect. But because we know that height at 1 is less than height at 0, we can actually automatically just extend it all the way to over here. Right? So what we're going to do is we're actually going to do something kind of unintuitive. We're going to, instead of say remove 0 and add 1, we're going to remove 0, so get rid of it, and then we're going to look at 0, because the index at 0, the height at 0 is the first height, because the height at 0 is the only height that is greater than the height at 1, we're going to include everything from the index 0 for our height 2 searching. So what we're actually going to do is we're going to insert 0 back in, and then we're going to alter our array. So I'm just going to get rid of let's get rid of these two top parts. So now, if I say height 0, it's just equal to 2, okay? Because, like I said, this being 4 is not relevant anymore. Because back here, when I already parsed 4, I should have said this earlier, but back when when I remove the 0th index, basically, when I remove this, I should be checking as well. I should be updating max. Basically, I should be updating max based on the index that I popped out, or the current index. So I'm gonna just say I is the current index. So right now, I is over here, minus the index, the popped index, minus the popped index, multiplied by the height at popped index. And we'll see why this makes sense in a second. But just for this case, for now, it makes sense, obviously, right? Because this I minus popped index just represents 1. And then the height at the popped index is 4. So this just represents the width. This is just the height. And then, well, the whole reason why it works is because we know we're always going to be dealing with a monotonically increasing stack, which means if we had multiple items of height 4 over here, if there are duplicates, I'm not going to change the stack at all. But I'm going to be referencing the very first index where the height 4 occurs. And then that will be what the popped index is. Okay, so in this case, max is updated to be equal to 4. And then we change the state of our array. And then we can increment I to be over here now. We increment I to be over here now, right? So continuing along, I'm going to move some things around. Continuing along, now we see this height, 1, 2, 3, 4, 5, 6, right? Height 6 at this index 2. So what we're going to do is we're just going to add index 2 because 6 is bigger than this height, which is 2, right? We updated the array. So now I'm going to go to the next one, add the index 3. So notice how it's still a monotonically increasing stack, right? It's not necessary. These numbers aren't necessarily going to increase, but the heights affiliated with these numbers must be increasing. So we continue. We don't update max. We only update max when we pop elements out. So now I goes up to here now, right? So here, once again, we see, okay, this height is smaller now. We're going to want to get rid of, just with some quick foresight, we're going to be popping this and this, right? Because this is smaller. So once we see it's, so we're going to first look at this height, this index 3. We're going to do the same thing where we say max is equal to I minus popped index times height of popped index, and that just gives us this piece right here. That's what that gives us, right? So once we get that, we say, okay, we found a new max. So now max is equal to 7, the height of that piece. But we do get rid of that piece. So we get rid of this because it's no longer usable in the future. Same thing as with what we did back here earlier. No longer usable in the future because we saw that there's a gaping hole right here. There will be no more 7 height options that go all the way, that extend all the way back to index 3, right? So same thing with 2. There are no more options here. But this time, when we do I minus popped index, it's going to give us this entire piece, right? It's going to give us this entire piece. So yeah, that would give us 12. And the reason why it gives us this entire piece is the same reason as what we looked at earlier, right? With this I minus popped index giving us the width. This is very crucial because the popped index is this index right here, is this right here, getting popped. So I'm actually going to put it back in. I'm just going to cross them out to represent they got popped. So those indices got popped. We don't care about them anymore. And yeah, there will be no more height 6 options that include index 2 as well. Same thing. Because once again, gaping hole right here. So now we see that the height, we're still working with I at 4, right? We're just tracing backwards. So now we see this 0 has a height of 2. 3 is greater than 2, right? This height right here is greater than this height right there. Actually, it's going to be this height right here, right? Or sorry, this height right here, right? So because we know that it's greater, we just add it in. But do not forget, we can't just instantly add in this, we can't just instantly add this I value right here. So what we tried to just do is add I. But because we know we popped 2 and 3, we use 2 as what we push in. Because we know 2 and 3 was greater. We know it was greater than, or we know the heights affiliated at index 2 and 3 are greater. So we know it can include this 3. So basically, we're going to do the same thing. We use 2 and we update our index 2 to reflect a height of 3. So we're going to be using this segment right here. Does that make sense? And if we run through this process, we're going to eventually see like a sort of structure where we're always, the last item we pop is going to be the new index that we push. So rarely are we actually pushing I in. We're only pushing I if we don't pop anything. But the last one we pop is what we push back in, and then we just update that value, right? Because the last one we pop, we know has a height greater, which means it must also be able to support this height 3 structure that we saw started at I, but really it can extend all the way back to I minus 2, so 4 minus 2. So if we continue this, let's move on to here. We see it's height 3. Like I said, if the heights are the same, we don't do anything. Go to here, still the same. We don't do anything. So now we go to here. We see 7. Do we have to pop anything? No, we don't, right? All we have is 0 and 2, which is just this and this. So it's still ascending. It's still a monotonically increasing stack, right? The whole point of this is a monotonically increasing stack allows us to only have to keep track of the most useful information. The other information is all irrelevant. We don't need to keep track of dips, right? We just need the best option. So continuing along here, at 7, we just put it in, and then it moves to 8. Put it in, it moves to 9. Okay. Or we don't put 8 in, right? We just skip it because it's the same height as the one previous. Once we reach 9, this is another big pivotal moment. Notice how we haven't updated max yet, but we are about to get our answer of 21 up here. So, right, using a monotonically increasing stack. So we see the height of 9 is 1, right? So that's our new limiting height. This height of 1 limits everything from before. So we're going to pop. We know that 7 cannot extend because of this gaping hole. Get rid of it. As we get rid of it, we multiply this index. So we multiply what we just popped. We take I, which is equal to 9. So 9 minus, remember our equation up here? 9 minus 7 equals, 9 minus 7 times the height at the popped index, 4, is equal to 8. So that's how we did everything back here as well. But right now I'm just showing how it would look over here. And, right, same stuff as before. That just, this 9 minus 7 just represents this width, and then the other one just represents the height. Okay, let's continue along. So now we don't update it because it's not greater than 12, not greater than the max. And get rid of 2. Let me change my color back. Get rid of 2. As we get rid of 2, we notice, okay, 2 is all the way back here. 9 minus 2 times 3 equals 7 times 3 equals 21. That's where we update our max, and that's where we find it. I mean, we don't know we found it yet, but the computer has found it. Found the solution, right? And then we have to keep on going. This 0 has a height of 2. We're looking at a height of 1 here, so we have to get rid of our 0 as well. So 2, so what would it be, right? 9 minus 0, that's the index of this 2 one, times 2, which is the height, equals 18, doesn't update. And then we add 0 back in, right? Why do we add 0 back in? Remember, because we used the most recently popped one. Because we know that the most recently popped one has a height greater than this height right here, so it can actually extend all the way back. We know that all the heights we popped have a height greater, so now we are just using this. This is what we are using right here. And we don't know where it ends, but we'll see where it ends eventually. So that's what the whole point of the stack is for. Notice how I don't draw this line right here. I don't draw it yet, right? I just store it right here. I keep track of the starting point of it, and then eventually I will come to a point where I find the end point. That's what I was doing with every single one earlier as well. I was keeping track of this open-ended segment. I did not draw this ending, but once I noticed that this height over here was less than this height, I drew this, and that's where I updated my max value. Because once I see this, I know, okay, this 3 is no longer viable as a height all the way back here anymore. And yeah, that's basically all there is to this problem. Once you see an example like this, I think it should become quite straightforward, and you can apply this and implement it yourself.